Okay, so now we're going to do an example which ends up using almost all of the properties that we've talked about earlier. One of the things I want to say before I go on is that you please make sure that you've clarified all of the concepts that we've talked about before this example. That's extremely essential in order for you to be able to understand what's going to go on in this example. So what we have is the following information that's given to us, as you can see on your screens. So we're told that there's a signal which is a periodic signal, and that periodic signal is real. So that's the first thing we know. The second thing we know about the periodic signal is that the period for that is equal to 4. The third thing that's given to us is that the Fourier series coefficients are equal to 0 for all values of k for which the absolute value of k is greater than 1. Okay, so that's the third information that's given to you. The fourth one, which may sound a bit convoluted, but here it is. It says if for a given signal with has a Fourier series coefficients bk, which where bk's are given related to ak's through this relationship, that signal which has the Fourier series coefficients bk is odd. And finally, the fifth point that we're given is that the average power in the signal, the x of t, is equal to half. Now, given all of this information, we are required to determine what the signal x of t is. So let's start with the solution. The first thing is, which is the information that's extremely useful, is so let me is the following. So the first thing we know is that the signal is periodic with the period t equals 4, right? So if it's periodic with a period of 4, let me try to find out what the frequency is. Omega naught is 2 pi by t, which is just equal to pi by 2. So this is the fundamental frequency of the signal. Moreover, we know that k equals 0 for absolute value of k is greater than 1. So this is extremely useful for us to know because that means, what that means is that the only Fourier series coefficients that I need to determine are a minus 1, a 0, and a plus 1. So these are the only three coefficients that I need to determine. And if I can do that, that means I know the signal completely, right? Now the analysis equation, the synthesis equation just tells us that x of t is equal to summation over k going from minus infinity to plus infinity, a sub k e raised to power j k omega naught t. But since the only a's that are non-zero is a minus 1, a 0, and a plus 1, so therefore I can write this as a minus 1 e raised to power minus j pi by 2t plus a naught plus a plus 1 e raised to power j pi by 2t. Right, so this is the signal that we need to determine, and it's clearly visible that if we can determine what a minus 1 is, if we know what a 0 is, and if we know what a plus 1 is, that's enough. That's enough for us to be able to completely determine what the signal is going to look like. Now, next, what we're going to do is we're going to try to look at these B's and try to identify the signal corresponding to these B's. So let's say that there's another signal, which is y of t, and that signal y of t has Fourier series coefficients, which are given as the bk's that are given to us. So this is bk is e raised to power j k pi by 2 times ak. And we immediately see that this operation here, right? So this operation here corresponds, so actually there's a minus k involved. Right? So it's a minus k here. So this corresponds to, from the shifting property that we know of, this corresponds to time shifting and what else? And time flipping. So where this minus k is because of the flipping in time, and e raised by jk pi by 2 corresponds to the fact that the signal has been shifted in time. That's from the time shifting property and the time flipping property or time reversal property. So what we really conclude because of this is that y of t is really time shifted and time reversed version of x of t, right? So that's something we can conclude. And there, since x of t is real, so we know that x of t is real. So y of t is just obtained by time shifting and time reversing of x of t. So therefore, it should be evident that y of t is also real. Moreover, we're also given the fact from 4 that is y of t is odd as well. So that's also something else we know about, right? So y of t is real and y of t is odd. And from the properties that we've done earlier, we know for a fact that that means that the Fourier series of coefficients of y of t will not only be conjugate symmetric, but in fact, they will be purely imaginary. So let me play around with that a little bit more. So from here, so y of t, so we conclude, so thus y of t is real and odd. And because it's odd, because y of t is odd, this implies that the Fourier series coefficients, or actually b naught, which are the Fourier series coefficient of y of t, is going to be equal to 0. Right, and that's once again, that's because of the fact that the signal is odd. And this also implies that b plus 1 is going to be equal to minus of b minus 1. This once again is because of the fact that the y of t is odd, and therefore the Fourier series coefficients are also going to be anti-symmetric. This is something we know from the properties that we've talked about earlier. From b naught being equal to 0, I can find that since b naught equals 0, I have that, and since bk equals e raised to power j k pi by 2 a minus k, we have b naught equals e raised to power j times 0 times a naught. And since b naught is 0, therefore this implies that a naught equals 0, right? So there you have it. So one of those three Fourier series coefficients we've already determined. So all we need to do next is try to determine what a plus 1 is and what a minus 1 is, all right? So from the same expression, so from this expression, so I know that b plus 1 is going to be equal to e raised to power j pi by 2 times a minus 1. And e raised to power j pi by 2 is j, so therefore this is j times a minus 1, and therefore this implies that a minus 1 equals minus j times b plus 1, right? Similarly, b minus 1 is e raised to power minus j pi by 2 a plus 1, and which is just equal to minus j times a plus 1, and therefore a plus 1 equals plus j times b minus 1, right? Uh, so these are the two expressions we have. Um, right. All right. So moreover, I know that since y of t is an odd signal, so therefore b plus 1 is going to be equal to minus b minus 1, which I've actually written over there, over here as well. So this implies that a plus 1 equals plus j times b minus 1, right? Which is equal to minus j times b plus 1, which is nothing but a minus 1, right? So this implies, so let me conclude. So thus, a plus 1 is actually equal to a minus 1, right? So the next thing we want to know about is what these, so there's only one coefficient that I need to determine now. That's just a plus 1, and a minus 1 is just simply going to be equal to that a plus 1 as well. Another thing I notice here is that since y of t is real and odd, since y of t is real and odd, b's, they are purely imaginary. Right? And since they're purely imaginary, and since a plus 1 equals plus j times b minus 1, this must imply that a plus 1, which is actually equal to a minus 1, must be real as well. So it must be real, right? So it must be real. So that's another conclusion we have. So we don't need to worry about finding the phase of A or the imaginary part of A. We're just going to find the real part of A, right? And finally, from Parsifal's relationship, so from the condition 5 that's given to us, we know that 1 upon 4 x of t absolute squared dt is equal to half. That's something that's given to us in the problem statement. From Parsifal's relationship, I know that this is equal to the absolute squared and sum over all the Fourier series coefficients. So this is equal to a1 squared plus a naught squared plus a minus 1 squared, and all of the other coefficients are 0. So this must be half, but then I know that a naught is equal to 0. I know that a naught equals 0. I know that a1 is actually equal to a minus 1. So therefore, I can conclude that 2 times a1 squared must be equal to 1 by 2, which implies that a1 absolute squared is 1 by 4. This implies that the absolute value of a1 is equal to half, which is exactly the same as the absolute value of a minus 1. Now there is a certain bit of ambiguity here. So where all we know is that the absolute value of A1 is half. Therefore, so A1 could, n is real. So A1 could either be plus half or A1 could also be minus half as well. So so here we can conclude that A1 is equal to half or A1 equals minus half. So there is this slight bit of an ambiguity here, which we will never be able to resolve from the given information, right? Nevertheless, we have been able to narrow down to what the Fourier series coefficients are. So therefore, remember the original problem statement was to try to identify what the signal x of t looks like. So x of t is remember, let me write out this entire thing. So a minus 1 e raised to power j minus j pi by 2 t plus a naught plus a plus 1 e raised to power plus j pi by 2 t. I know that this is equal to 0. I know that this is equal to either plus or minus half, and this is equal to either plus or minus half. So therefore, x of t is equal to e raised to power j pi by 2 t plus e raised to power minus j pi by 2 t times either a plus half or a minus half. So therefore, from Euler's identity, this is either plus cosine pi t by 2t or minus cosine times pi by 2t. And there you go. So I understand that this example may have been a lot more involved than some of the things that we've done earlier. And that's why I want to make it clear. I mean, you need to make sure that you understand all of the concepts we've done before this, before you jump into this. But once you do get this, this would make me extremely proud.